Hi, my name is Colin Magdamo, and I'll be talking about natural language processing for detection of cognitive concerns. We have no disclosures for this work. Dementia is under-recognized, underdiagnosed, and undercoded in claims data by healthcare professionals. Dementia-related diagnostic codes and medication records can miss many cases of cognitive dysfunction, but a wealth of information is contained in unstructured clinician notes within electronic health records. In order to comprehend this unstructured data, manual chart review by experts is often employed. However, this is time-consuming and potentially error-prone. Automated mining of these clinical notes presents a potential opportunity to label patients with cognitive concerns who could benefit from an evaluation or be referred to specialist care, and to provide better phenotyping for research studies using the EHR. To address this problem, we developed NLP classification models to classify a binary measure of cognitive concern using a gold standard dataset that was curated by a team of clinical experts. Our baseline model was a regularized logistic regression with structured variables that are commonly used to try and identify patients with dementia, these being diagnosis codes and medications. We then compared this baseline to a model that used counts of regular expressions related to cognitive concern that were curated by experts, and a model that used TF-IDF vectors. Finally, we used the deep learning transformer-based model. The visual on the bottom right shows our different regular expression categories used in Model 2, and the percentage of patients out of 767 that have at least one instance of this regular expression category for each level of our outcome. This demonstrates that the simple regular expression categories have a relationship to our outcome of interest, although when classifying cognitive concern, context on both the local and global levels is extremely important, and this fact motivated our deep learning approach. Our deep learning approach used a previously developed transformer model called Longformer by Allen AI, which accommodates long sequences such as concatenated medical chart histories by utilizing a sliding window approach. Longformer uses different attention mechanisms relative to previous transformer models. These mechanisms consist of a local attention as well as a global attention to a select few tokens. When combined, they remain expressive but do not scale quadratically with input length like previous models. Longer sequences are broken up into shorter sequences with 20% overlap, and then each shorter sequence is classified before a final aggregation of the window-level predictions to the patient-level predictions. Currently, aggregation is performed using the mode of the window-level predictions, and we are investigating alternative aggregation functions. Longformer is similar to a landmark pre-trained transformer-based model developed by Google called BERT, but Longformer has the capacity to operate on longer sequences. The AUCs of our models are listed in the table, and our transformer-based model achieved the best performance with an AUC of 0.93. The sensitivity of the deep learning model was 0.74 versus 0.59 in the baseline model, with a relatively small decrease in precision. It should also be noted that our outcome of interest is binary classification, and while even simple methods using structured variables can have similar performance to deep learning, classifying the particular stage of cognitive decline will necessitate a much more expressive model that can leverage more context, as the clinical distinction between stages is significantly more nuanced than an overall impression of cognitive concern versus no cognitive concern. We expect the deep learning to outperform other approaches by a wider margin as we expand the sample size, as well as increase the difficulty of the classification question. It should be noted these measures are evaluated on a small test set of size 77, and future directions include expanding our sample size via active learning. To expand the sample size and collect detailed information regarding staging, we've prototyped an annotator web app that memory experts can use to rapidly conduct the chart reviews. In the annotation tool, regular expression key phrases of interest are automatically highlighted, thus improving the efficiency of the typical chart review process. Patient syndromic diagnoses will be labeled for each year, and some individual notes will be labeled with a binary indicator for cognitive concerns. Using this tool, the patients with low confidence predictions will be labeled by experts to improve model performance using an active learning loop. We will investigate model performance and query individuals with characteristics that the model performs poorly on. In conclusion, this work will improve the efficiency of expert adjudication using our annotation tool. In the future, it will provide a better understanding of the predictive value of structured variable-based phenotyping of dementia in research studies, and has the potential to help us understand the nature and magnitude of biases in the EHR. In clinical settings, NLP-based case identification could be used to identify patients with cognitive concerns who might benefit from cognitive screening or specialist follow-up. Thanks to all the listed acknowledgments and for all their help and insight, as well as the listed funding sources. Please reach out to me with any further questions.